Welcome to the first lesson of Unit 5. And to this point, Units 1 to 4 have involved us looking at the concept of a derivative, understanding what it is and what it represents. We have also taken a look at differentiation rules, the various tools that allow us to investigate the derivative of every type of function we're going to see in this course. And so now, getting to Unit 5, we're going to start looking at some of the general applications for the derivative. We've already investigated one big one, which is the idea of position, velocity, acceleration, and so you already have some of the base concepts that we're going to be using throughout this unit. And where we'll get started is the idea of extreme values. And so what we're going to investigate first is the idea of extrema. When we talk about extrema, we're going to see two types. The first, what are known as our absolute, or you'll also see the word global extrema. And what absolute extrema are, it's the highest, or the word we tend to use for that, maximum, or lowest are minimum values for a function over its domain. So if we look to the graph on the left, we will see that this function takes on an absolute maximum here, and it has no absolute minimum, no lowest possible value, because the range of this function takes it down to negative infinity. And the other type of extrema we're going to see are our relative, or the other word you'll see is local extrema. This will be function values that are higher, so there's our max idea again, or lower, minimum, than all nearby function values. So it doesn't need to be the absolute highest or lowest, it just needs to be higher or lower than everything close by. So if we look on this graph again, we would see a relative minimum here. Think about this idea will be peaks and valleys. So we got a nice little valley, a relative minimum. We got a peak coming up top. Here is a relative max. And we've got a couple more. Another relative min, and a final relative maximum. Notice this absolute maximum that we started with would also be a relative maximum as well. And so where we'll wrap up on the basic information is our big concept, and really one of the bigger concepts that's going to allow us to talk about derivative applications, what are known as critical points. And what critical points are going to mean to us is points where a function can have a maximum or a minimum. Critical points are going to happen at certain locations along a function. So critical points can occur when, well, spot number one, and this is one we've actually seen before, where the derivative of our function equals 0, or our tangent slope is 0. And so if you notice, 1, 2, 3, 4 of these extrema occur at spots where the derivative equals 0. The second place we can find critical points is where the derivative does not exist, but the function is still continuous. So, a cusp or a corner, like we see with this relative max right here, it occurs at a corner. And the third are going to be endpoints of a domain. But with this, only absolute extrema can occur here. Relative extrema require a graph on both sides, require a two-sided limit. Whereas the absolute highest or lowest function value could occur at endpoints if we close off an interval. And so these criteria are what we're going to want to keep in mind as we go forward. Let's go ahead and put that into practice, see if we can identify critical points given a function. And let's start with graphs. So looking at our first graph, notice domain negative infinity to positive infinity. So how I'm going to think about critical points are in three ways. And you're also going to see this when you get into your practice. I've kind of organized it this way every time. The first thing I'm always going to look for on critical points are the endpoints. And since this has an unbounded domain, there are no endpoints, and therefore that will not add to my number of critical points, where my derivative equals 0. I see one spot here that would have a horizontal tangent, and that occurs at x equals 3. And finally, where the derivative does not exist, well, this looks like a nice smooth curve, no sharp corners, cusp, no discontinuities, so there are no spots where the derivative does not exist. So finishing up our analysis, now that we know our critical points, we're going to label what they are. And so x equals 3, that would be a relative minimum and also an absolute minimum. It's not just smaller than everything around it, it's the smallest possible value taken on by the function. Looking on to our second graph, notice this one does have a half-closed domain, going from 2 to infinity. So we're going to start off getting our critical points. And let's start with ends. Well, we do have one endpoint here at x equals 2, so we're going to want to note that one. Spots where the derivative equals 0. I've got one here at x equals 3, and spots where the derivative does not exist, we have none. So breaking down what's going on with our various critical values, at x equals 2, well, that's nothing. At x equals 3, though, we're going to have a relative and an absolute minimum occurring right here. And on the next graph, notice we have a domain from 2 to 5, including 2, but not including 5. So our critical points, looking at the ends, now I'm going to put down both ends. I'm going to put down x equals 2 and x equals 5, even though on this one, note, it is not defined, which means if a relative max-min or absolute max-min looks like it would occur there, we actually wouldn't have a max or min then. Where the derivative equals 0, once again at x equals 3, and where the derivative does not exist, we have none of those. Breaking down our various points, x equals 2, well, that's nothing, not higher or lower. X equals 3, once again, going to be a relative or absolute minimum. And when we look at x equals 5, what we're going to note is it would be the absolute max of the function, but it's not defined, which means x equals 5 would actually be nothing, and we wouldn't have an absolute max for this function. And so what I'd like you to do, go ahead and pause the video, and for these last three functions that you see here, see if you can spot all the critical values for these functions, and also see if you can break down the locations of all relative max and min, and any absolute max or min that might exist here. Go ahead and pause now, and when you're ready to check your results, unpause the video. Okay, so you'll notice I changed up how I wrote my results a little bit just to keep it organized and show you I am considering every type of extreme that we might run into, absolute max and min, relative max and min, and hopefully your results come pretty close to mine. Where we might have disagreements is maybe where these particular x values are located. I said about 2.5 and 4.1. If you're anywhere close to that, that's fine. So please make sure to pause the video again in case you need to get this information copied down or corrected. But if you're ready to move on at this time, there's only one more big thing dealing with the introductory information, and you'll see that's right below what's known as the extreme value theorem. And it says that if a function is continuous on a closed interval specifically, then you're guaranteed to have both a maximum and a minimum value on the interval. Even going a little extra, you can say that you're guaranteed to have an absolute maximum and minimum value on the interval. So if I zoom back out, and you can get a look at all 6 graphs at once, notice the domains. There was only one graph that had a completely closed domain, and notice we had both an absolute max and min for that graph. If you look right next to it, we had a domain where only one end was closed off. We were able to get an absolute max, but not an absolute min. And on our last graph down here, we were able to get both an absolute max and min, but it was never going to be guaranteed because this wasn't a completely closed interval. The three graphs up top, two of them were unbounded in one direction, which immediately provides the chance that, and take out the possibility for having an absolute max or min. When you're asked about finding extrema, if you're working on a closed interval, you're already guaranteed that those results are going to exist. And now moving along, let's take the graphs away and see if we can still run the same kind of function analysis to find extrema for a function. So if I look at this function, f of x equals 1/3 x cubed minus 9x plus 24, think about the main places that we can find critical points. We can find them at endpoints, where f prime equals 0, or where the derivative does not exist. Well, this function immediately has no endpoints. I didn't give you boundaries for the function, and everything else goes off of looking at the derivative. So the derivative of f of x will be x squared minus 9, that 24 will go away. And we're looking for two things. And so let's set up the same analysis. Our critical points, well, for the end, we have none. For f prime equal to 0, well, that's just going to involve setting our function equal to 0. And this is one we could factor or solve algebraically. I'm going to tend to go toward factoring. And we'll get 2. We'll get 1 at x equals 3 and 1 at x equals negative 3. And dealing with the f prime does not exist case, that's one where we've got to have a good understanding about our functions. And notice how this is a polynomial. It exists for all values in the domain. We're not going to have to worry about this last one. And so our critical values are only x equals negative 3 and x equals positive 3. And so let's try this one more time. We got g of x equals 1 over square root of 4 minus x squared, or 4 minus x squared to the negative 1/2. And so g prime will be negative 1/2, 4 minus x squared to negative 3/2 times negative 2x. And let's get that simplified to make our upcoming calculations easier. These negatives will cancel each other out, become positive. The 1/2 and the 2 will cancel, and we'll get x over 4 minus x squared to the 3/2. Breaking down our critical points, well, for the end, I did not bound this off, so there are no endpoints. Where f prime equals 0, well, notice how this is a fraction. And for a fraction to equal 0, we specifically want the numerator equal to 0 without the denominator equal to 0, x itself equals 0. And for the does not exist case, again, being a fraction, where this thing will not exist is if the denominator is equal to 0. And specifically, if that inside function equals 0 down here. And that will happen when x equals plus or minus 2. So putting that together, our critical values will be x equals negative 2, x equals 0, and x equals 2. And moving along, let's put what we just did into use and try to apply that to find absolute maximum and minimum values on a function, keeping in mind that these max and min values can only occur at critical points. So we got to find our critical points. So we'll find our derivative first. That'll be our first step once we talk about max or min from here on out. We'll get 3x squared minus 6x. I'm going to go ahead and factor this in advance, knowing the type of analysis we have to do. And let's set up our chart. Well, for endpoints this time, we do have two. We have x equals negative 1/2 and x equals 4. For our f prime equal to 0 case, we're going to be setting our derivative function equal to 0. And our first factor, this 3x, will equal 0 when x equals 0. And the x minus 2 factor will equal 0 when x equals 2. And for the derivative not existing, well, that's not going to happen. This is a polynomial. And so the way we can figure out where we have our absolute max and min, think about, I only have 4 possible spots where this could happen. And so the easiest way for me to test this out is, I'm just going to go ahead and set up a table of values using these 4. So there's all my x's. And now I want to get my actual function values, because that's the big thing. It does say find the actual max and min values. Those are going to be values for y, or f of x. The x values are just where the max or min are located. And so I'm going to take each of these x values and plug it back into the original. Now on some of these, if you need to go ahead and use a calculator to figure that out, go for it. With this first one, f evaluated at 1/2 will give us a positive 1/8. F of x evaluated at 0 will equal 1, and so on down the list. And what we're looking for, we are looking for the highest and lowest outputs. This is a closed interval, and it's continuous, so extreme value theorem guarantees we're going to find those. At 2, we're going to get a -3, and at 4, we're going to have 17. Our absolute max will occur where we had that output of 17, so at 4, 17, and our absolute min will occur at 2 with a value of -3. And so what I'd like you to do, one more time, go ahead and pause the video, and let's see how far you can get through the one on the right on your own. And we'll do this in stages. The first time you restart the video, you'll see my initial breakdown of where the critical points are. I'll give you an opportunity to pause one more time, and then you'll see my breakdown for how I figure out where your absolute max and min occur. So go ahead and pause the video, and restart when you're ready. Okay, so taking a look at my results, notice my derivative function. Hopefully we were able to get that accurately. And notice my rewrite, getting rid of that negative exponent to make it easier to read. Had the endpoints that were defined at the beginning as -1 and 3. I found f prime equal to 0 when I set the entire derivative function equal to 0. And for where f prime does not exist, notice you did have one spot where you were dividing by a variable. Notice that x to the 1/3 is what will cause this derivative to not exist when x to the 1/3 equals 0, which will happen when x equals 0. So go ahead and set up your table with all of your possible locations for the absolute max or min. Go ahead and try to get those calculations on your own right now. Pause the video, and when you're ready to see the final results to this problem, go ahead and restart. Okay, and so notice I definitely used a calculator to figure out f of 3, and the absolute maximum occurs at 0, 0, so my biggest value is 0, and my absolute minimum occurs at -1, -5. So the last thing I want you to do is find the extreme values for these three graphs, which means the y values, and where they occur, at which x values. Keeping in mind this can happen at endpoints, where the derivative is 0 and where the derivative does not exist. So for the last time in this video, is pause the video, try to find the solutions for each graph on your own, and restart the video when you're ready to see the results. And what I'm going to do is give the results for the graphs one at a time, so that you can check your solutions one at a time. Go ahead and pause and try the first graph now. So our results for graph 1, notice the absolute max is also a relative max in this case. There is an absolute minimum. There are no relative min, because even though I have a spot where the derivative does not exist, over here at 1, the function is not continuous there, and so that negates the possibility for a relative extreme. Pause again, and come back when you're ready to see the results for graph number 2. And once again, the absolute max in this case and the relative max are the same thing. There's also an absolute minimum on the left endpoint. And once again, even though you might be thinking a point like this could be a relative min, for relative extrema, the two-side limit must exist. It must be continuous there, which means we have no relative min. Pause one more time, and then restart to check out the third and final graph. And once again, we have both a relative and absolute max at the same point. We do have an absolute minimum value occurring right here at this defined lowest point, and once again, no relative min in this case. And so that will do it on lesson 5.1. A slightly bigger lesson because we had to make sure we got the main vocab out of the way and get a clear understanding about when and where both absolute extrema and relative extrema can occur. So please make sure that you review and summarize your notes. Make sure you're very clear on the various vocabulary and types of problem situations that we've encountered. And when you're ready, please move on to the practice for 5.1. Thank you for watching.